Hey everybody, welcome to PCB Routing on Saturday. This is the fifth episode already, and the second episode on the USB thermocouple. I'm Odin. I have about 25 years experience making PCBs and about 5 episodes worth of experience streaming stuff. So sorry for any technical glitches, but hope my PCB knowledge is up to snuff. Let's get right into it. So here is the board as we left off last week. The only thing I added was the debug connector. Um, that was a lot of clicking because I had the normal 6-pin needle adapter has holes, but we don't have enough room on our board for the holes for the teeth to click in. Um, this is to debug the rp2040 microcontroller. And so what we've done with the smaller boards is just leave the teeth off, and then you have to build some kind of a jig that will hold it on, or tape it on, whatever, while you're debugging. There's no real other way to do it to be able to fit it in the tiny case. I've had some ideas in the past about using some of the unused pins on the USB connector to route the single wire debug lines in through that. Uh, then it's not, I guess, technically to standard, and you might have some weird issues with other people doing other things on those pins. Also, that, well, yeah, okay, maybe you have the CC2 pins. If you were to pull one of those, I don't know, negative 10 volts, then multiplex it in or something, then you kind of get around that. But yeah, that's kind of a side quest that maybe I'll get into on a much later episode. For now, we'll just find some space on our board to put that. Um, it's Yeah, it's going to be hard to get it to fit on the board because we didn't think about it in advance. The RP2040 can also be programmed over the USB, but I think you can only do that once because after that, your program is going to be using the USB, right? And so only when it's empty can you program. And also, you certainly can't, stepping debug or anything like that. And we probably want to do that developing firmware for this. Although, for this project, maybe we don't need to, but yeah, I mean, we definitely have some room on the board for the debug connector if we scooch a bit. We have some more components that we just didn't have time to place last time. Um, I had originally thought we were going to need 3 episodes to do the thermocouple, but since we used the edgy boards, that made it go quite quickly doing the schematic. So just to get everybody back into the mindset, we have a USB-C connector, we have ESD suppression. Um, yeah, yeah, if we have some overvoltage or whatever, you're probably not going to expect overvoltage over USB because you're so far away from the outside where there could be lightning or something. It's just going to be people touching it that are statically charged. And so we have a diode that just swallows that energy and turns it into heat. So that's our protection on the USB connector. We also have, on the other end, we have these 2 test points, which is where we're going to solder our thermocouple connector onto. Um, we need to make sure that if somebody touches that end, that ESD is not going to fry our chips. Most chips actually these days, back at the beginning of my career, this was different, but these days most chips have ESD protection on every pin already anyway. Um, just so that handling boards and whatnot doesn't fry stuff. Uh, I would still advocate for putting it on the other board because things like a capacitor is not going to have ESD protection. I mean, obviously it's got to be a pretty small capacitor because the human body model is yeah in the lower nanofarad range, right? So as an American, I know there are very different sizes of humans. Ha ha ha. No, but the capacity of human is not huge compared to a capacitor, and there's going to be some losses on the way in. So yeah, if they're big capacitors, they'll just slurp it up the energy and won't be a problem. But small capacitors, they don't have any intrinsic ESD protection and whatnot, and it's ESD protection's cheap, right? It's not going to break the bank. I think this chip is well, we could actually see what this chip is in a minute. Um, uh, Later, we'll be going to be selecting components and we'll see what it is. But my guess is something like 15 cents, 10 cents, maybe not even that. The Chinese prices are actually better than DigiKey considerably if you're, buying in China for the uh, PCB assembly, then stuff just gets dirt cheap. Okay, so that's the SD protection. Then we have our relatively simple input circuit for the thermocouple. Basically, the way the thermocouple works is you have two different metals. Each of those metals will have different number of electrons in the outer shell. From that, you have a kind of a natural uh, imbalance in voltage across the two metals at different temperatures. The I'm sure other people on YouTube will explain the whole principle way better than I can, but in my sort of engineering caveman brain, you connect the two wires and they have a voltage, and there's a table lookup table which goes from voltage to temperature, right? It's not quite a linear curve, but the voltages are very small. So we're talking low millivolts. So to be able to digitize that, we need an ADC that can deal with low millivolts, which usually means it's gonna have to have some kind of gain amplifier built into the ADC. You could do that externally, and back in the day, we did do it externally. Um, like you could set up an op amp and configure it to amplify the signal and all that. But anymore, just buy an ADC with an op amp in it, right? Then you don't have to worry about getting low tolerance components. You don't have to worry about people touching the board. That kind. I mean, it. We're kind of at the edge of the level where you do have to worry about fingerprints, conductivity, and whatnot. If you're such low voltage, right? If you're amplifying something by 100x and then only looking in the 100 millivolt range, then yeah, yeah, dust building up on resistors and stuff plays a role and blah blah. So yeah, you don't want to have to think about that. Uh, um, so yeah, another Odin the Nerd tip: just use an amplifier that has the gain array in it, and then you don't have to worry about it, right? You also don't have to worry about ESD and all. Yeah. So yeah, so we have an ADC which is kind of built for this, right? It's got a temperature sensor built into it. Oh yeah, that's the second thing you need to know with the thermocouple. You need to know the voltage, and you also need to know the temperature at which you have a junction between the special metals and copper, right? So if you have a temperature sensor in the ADC, it's not going to be exactly the same temperature as the connector, right? Or the place where the connector is soldered to the board, but it's going to be pretty darn close, right? If they're pretty close to each other and there's not something else going on the board or whatever. Um, so yeah, the ADS 1120 is probably kind of meant for that. I mean, there are actually a lot of other precise sensing things where you do need to know the internal temperature. Like, the joke is everything's a temperature sensor. Some things also measure other stuff. Uh, yeah, almost every process changes with temperature in electronics. And so, yeah, it's not that the ADS 1120 was specifically built for thermocouples or anything, but it's definitely built for precise measurements of low voltage stuff where you are interested in a temperature. So yeah, so we're using that. I had some suggestions after last time that I should just go with the like there's a prepackaged thermocouple chip. I'm forgetting the name, the part number. But the thing is that that chip is more expensive and less accurate than this ADC. And besides the ADC, there's just some, yeah. I mean, the thing with the ADC is you do have to do the lookup table in software, but I've already done that, so yeah. I mean, if you're looking for simplicity, maybe just go with a prepackaged thermocouple sensor. But yeah, no, I mean, the manufacturer of the thermocouples will publish the lookup table, and making a lookup table in software is actually not that hard, right? So um, yeah, so that's how we're going to be turning temperature into well, first into ADC values and then into digital temperature. Um, so switching back to the PCB, we have some components on here which will be routing shortly, which we just didn't fit on, and we have the debug connector, which we'll probably have to scoop stuff around to make that one fit. So yeah, so I hope everybody's kind of caught up from last time. Last week stream didn't work out. I have family visiting from overseas, and I just didn't find time. So sorry for not being a reliable streamer. I don't do this professionally. I'm just doing this for fun and to help people. So yeah, sorry about that. Anyway, um, so yeah, let's get routing. I think we should probably. What are these? Reset. Oh, okay. So this is just the yeah, 10K pull up, and then that's probably a capacitor. Yeah, capacitor on the reset line to keep it from being moved around by uh, stuff going on in the environment, right? Like if you have big voltage shifts in the environment, there might be capacitive coupling to the reset line, and so if you don't have a capacitor on there, then theoretically something changing in the area could cause a spurious reset. It's really annoying when that happens. I only had one design in my history where that actually became a problem. But and in that case I did have a capacitor on the reset. It was just too small, and the reset line went way across the board, and so there was a lot more potential for capacitive coupling. So if I had, something like way over 20 centimeters away and I made that reset line go all the way across the board, then I also had some relays that were switching AC voltage on and off, like, mains voltage. And even though they're pretty far away, the if you just switch a relay on like mid phase, then you have a really really long and steep change in voltage, right? You have a steep flank because you don't. Yeah, I mean the trick that I should have used in retrospect would be to sense the phase of the mains voltage and then switch the relays when they're going through the zero crossing, right? So when they don't have any voltage potential across them, that would have been the smart way to do it. I famously am not smart, so I didn't do it that way. And so yeah, I had to end up kind of armoring my circuit from the EMI that I was producing by switching the mains voltage with the relay. And yeah, I had to up the size of the capacitor on my reset line. It took me a while to figure that out too. It was just, it was now and then, obviously, whenever the relay switches at the exact right phase of the mains voltage, or mains current, yeah, voltage, sorry, um, then it was resetting itself. So yeah, so that's why you put the capacitor on the reset pin, just to make sure that the surroundings don't mess with it. So let's see. So we're routing this up into here. And I didn't select a width, so that might be super tiny. I think 2 is a better. W selects the whole thing in KiCad. That's definitely a good one to remember. Oh, that's actually super fat compared to all the other stuff I routed. Yeah, I like uh, 0.02. I'm not sure if it's actually there's a good reason for it, but just seems like a good track width. Um, and pretty much any manufacturer will be able to do a .02 track width. Oh, I've got the follow the previous width on this thing here. If you turn it on, then it'll make new tracks in the width of the old tracks rather than what you have selected over here. So sometimes that's good, actually, if you have, different nets with different track widths and whatnot. But I usually just go and do everything that I can. Like, if there isn't a good reason, then I'll just do everything in .2. Yeah, like this ground could obviously be .2. This, yeah. Okay, so this is the SVWD stuff. So these are the debug lines. You do kind of have to be careful because these do get up into the many megahertz, 100 megahertz or whatever. You can set your debugger to do them in different frequencies. But yeah, the higher you can go, the better life is, right? You Yeah, your stepping debugger will just be a lot more reactive, and you'll be able to read the contents of registers better. And yeah, I think we're gonna have to scooch the crystal up. I'm not even sure why I did the crystal that far down to begin with. So let's do that. Sorry about that. I've been out all day, and I think I'm allergic to something. I don't know what I'm allergic to, but now and then it gets me. Okay, let's see. Let's just scooch all of this up. We do that, yeah, let's just unroot all of the nets. Unroot all the things. So we can move this up. So this is just decoupling to ground. So we could actually just do that one, like, because it doesn't, actually it probably should be that ground. So we'll just put this like this-ish. I guess we don't really have, I mean, we've got a bunch of SPI stuff going over here, but there's plenty of room up there. So let's, speaking of room, last time we looked at the JLC via specs, like minimum via specs that they can produce, the smallest vias that they can produce, and they were a lot smaller than I remembered. Well, they were a lot smaller than I remembered because those specs cost extra, right? Now I was remembering what the smallest spec was that didn't cost extra. Uh, at the end of the day, it doesn't cost a whole lot more, but yeah, these tiny vias, they're gonna charge you a couple bucks extra for the board with the tiny vias. So that's why it wasn't intuitive to me. I might go through and make the vias bigger, just if this is production design, because the half an hour that would take me to reroute all the vias to be bigger size, that spread out. I mean, I'm not sure how many of this product we're going to sell. I mean, this was just kind of a let's have a simple design to show people. But yeah, I mean, some products you sell tens or hundreds of thousands of them, and obviously, half an hour to make the vias cheaper is definitely well invested in that case. Um, the other thing that I noticed while I was looking at that was I've been telling everybody not to do vias in pad because it costs more. And that's probably still good advice, but because many companies still do charge extra for that, but JLC doesn't anymore. Um, JLC will give you tented vias, as in ones where the solder doesn't run into it, for free. So yeah, you can do via and pad. Now, there still could be concerns with like really small pads because the via is still not going to be as flat as the pad would otherwise be, even if it's like tented. So, still, uh, if you can avoid it, but definitely like in big pads, you can do vias. But yeah, I still kind of steer away from it because I'm worried I might need to find a second source for my PCB, even if JLC is um, if it's free at JLC, it might, especially with all the geopolitical stuff going on. I definitely don't want to make this into a political ordeal. It's just to share engineering knowledge, but I think generally people need to learn how to disagree peacefully a lot better anyway. But yeah, there is some risk there, right? Uh, whether warranted or not, that there could be some beef with China, and so yeah, definitely, don't. I mean, even though that's the China not China thing, there are other, like, your PCB manufacturer could just go bankrupt, right? We had a supplier go bankrupt recently, and it's not fun. Um, so yeah, try and keep, even if you think you know who you're going to be manufacturing with, try and keep the specs as buildable as possible. So yeah, I still probably suggest against doing via and pad, but apparently, I mean, engineering advice expires because engineers actually solve stuff, right? In contrast to some other disciplines, right? Our field evolves because uh, and the advice in the field evolves because people people made VN pads cheaper, right? So eventually, no one's going to have to worry about that, and the advice will be outdated. So yeah, keep that in mind. Like, if you're watching this in 10 years in the future, then while you're watching this, somebody probably made a better video. But also, that advice is probably expired. Like, probably everybody does tension V is cheap enough that it's not think not worth thinking about it at that point. There's been a lot of stuff like that over my career. Like, uh, old guy talking about war. Uh, back in the day, something like this would be frowned upon because this 90-degree angle, depending on like how the acid ran off the board, it could get caught in the 90-degree angle and kind of etch out like a little bit more than it should have. That like used to be a problem like way back when. And so my career started as that advice is probably no longer relevant was kind of the inside scoop, right? This is, I mean, nobody talks about this anymore. Nobody teaches this anymore because it's just not a problem. I mean, engineers figure out how to do it, how to make PCBs where that just isn't a problem anymore. And I think, VN Pad might go that route at some point, but yeah, it still is relevant today. Okay, let's see. Switch to the top with V. Make track with X. Keyboard's just way more expressive than the mouse, so yeah. Using the hotkeys, I definitely recommend. Well, I guess I've said that like 20 times already on previous streams. Oh wait, why is the 3.3 volt not connected to anything? That is sus. Let's see. Let's switch back to here. So that's going to be in the... Wow, wait, why isn't it? So it's called 3.3 volt V. Let's put the little highlighty on here. Highlighty thing is actually cool. One thing that took me a while to figure out is you have to turn the highlighty thing back off, otherwise you can't go up a hierarchical sheet with the highlight like enabled, right? So you have to escape and then go up, and then it'll still be highlighted. Okay, so why is... Oh, yeah, well, that's... well, there's your problem. We're plus 3.3 volts there and plus 3v3 here. So those nets are not connected. Yeah, I think putting the the letter in the thing as the decimal point for like capacitors or voltages or whatever. It's clever because it saves one keystroke, but on the other hand, all the new people don't understand what the hell you mean. And it's also not, I mean, I guess it's at this point, machine readability, you could just put AI in between and AI would figure it out. But uh, yeah, I advocate for, I mean, our style guide within the company, we definitely force everyone to put a decimal point in because the bottleneck is not typing, right? Like it's not like, oh, we could crank out a whole bunch more designs if we only could type faster. That's not the problem. Problem is almost always misunderstandings, as was the case here. So yeah, definitely um, put decimal points in is my advice, and don't do the clever uh, putting the letter in as a decimal point. Okay, well that is, I think, copper poor anyway, so we just have to put a via somewhere. I don't like putting vias really close to these pins because when you're trying to connect it, it kind of scratches around. And yeah, somehow it busts up the vias, like the pogo pins bust up the vias more than they bust up the tracks. And so, yeah, it might just be superstition, but I have worn them out in the past. So yeah, I try and kind of keep the vias a little further away. Okay, so what are we still missing? Gotta do the SBI, but I think I want to make sure all this fits before I really get going on the analog side. So what is all of this? I think this is yeah. So I think we probably want to do this somewhat symmetrical. I mean, like we want to put these two next to each other. Not that it really matters, but yeah, just so stuff is pretty. Let's see. Okay, so that's the 1 ohm. That's the other 1 ohm. And then after those two, we got that. And then this is, okay, this is just the bias, so that doesn't really matter where that goes. And then wait a minute, why is that pulled up 10K? Oh, that's the voltage divider. Okay, I got it. Yeah, so we got the voltage divider on the one side, so it doesn't kind of move out of the measurable range. So it's not really important where the voltage divider goes. Like you're not worried about uh, resistance or anything when it's already going through 10K of resistance. So what is this? This is probably a decoupling, but no, this is a ferrite bead. Okay, so this is isolating the analog from the non-analog stuff. Maybe we should put, I guess if we put that on the other side, then we have the analog net over next to the digital data lines. So I guess this is cool over here. We could scooch these all the way up to the top though. They definitely don't need to go that far down. Just to make some room for the other analog stuff. Yeah, the D key will drag it with connections, but then you kind of have to help it along now and then. Okay, so it's warning me about the edge of the board there. We do have to worry about the edge of the board because this is actually all not as intuitive as you might think. Like everything is so tiny. We want to be able to V-score the side of the board. Like if you're making things in batches, which this is definitely going to be, a batch thing because they're tiny, right? It's the pick and place machine is going to want to do a bunch of them at a time, and so you're going to have them in a batch, and so they're going to be connected together. And so the question is, well, how are you going to connect them together? You can do what's called mouse bytes, which basically means you have a router cut all the way around the board except for a little part, and then you drill holes in that part so it's easily breakable. Um, that does mean that you have to break them when they come to your shop, right before you solder them in, and that takes some time. But also, breaking them can also bend the board to where maybe some component, some pad pulls off the board or something because you're flexing it across some chip. And yeah, there's all sorts of problems that you can introduce with using mouse bites, and also they are like a stick, they stick out of the side of the board, right? So, um, where would we put the mouse bites on this board? We're going to be slid into a tube, so if we put them on the side, then that's, we'd have to sand them off or cut them off or whatever in house. And sanding PCBs in house is problematic because the PCB is made out of resin and fiberglass, and so if you sand the fiberglass, then you've got glass sand, and if you breathe that in, that's just, I mean, your body can't do anything with it. It's just going to be in your lungs forever, right? So you definitely don't want to breathe that in, and it comes with all sorts of problems. So V scoring is a little different. They cut the PCB from the top and from the bottom with like an angled cutter, and so the very sort of middle of the PCB is still connected, but the top and bottom have been cut, and either you can break them just by bending it, right? Or they also have, if you're worried about your PCB flexing, which you probably should be worried about, they also have these cutter things where there's like two little wheels that go from the top and the bottom and separate the PCBs that like push them apart, right? And so we do need some space for that to happen here on the side of the board, right? Like just the V cut will take away some of the room here. And so yeah, these components are getting pretty close to the side of the board. That's good that KiCad is warning us. So yeah, that's kind of a design for production thing that we need to be mindful of, because yeah, I mean, my first boards, I didn't think about that kind of stuff, and they ended up costing considerably more to manufacture than they could have. 2020 hindsight, now that I've figured out why why they were expensive and whatnot, right? Okay, so connected to this, I have the 1 ohm, and then the bias. Wait, I got the bias on the outside? Okay, I guess that's fine. The bias being on that side doesn't really matter. 1 ohm. 1 ohm on one side or the other is not gonna change much. So I guess maybe I'm gonna slide this one in so it's like this. Why is it snapping? That's kind of weird. So slide this one in so that they're kind of, let's do the G here, because we got tracks on it. G brings the tracks along with. Okay, let's slide that on there. I guess we probably want to move that a little way. Okay, then we'll set this one up so it's just below that, and then scooch this one down so it's just touching that. Yeah, I mean, most of the courtyards are a little more than you need anyway. I mean, anywhere pick and place machines don't need a whole lot of room to do stuff. Okay, so we got the other 1 ohm. We could put that here. That is pretty darn close to the programming connector. I don't know if we can really do it all that intelligently in any other way. I guess I could put this on the bottom of the board. Maybe I'm going to do that, because this is kind of screwing everything up. And it'll give me a chance to talk about more strategy. So, I probably should mirror it in the schematic too, because it doesn't really matter which side these are going through on. It's oh, let's see. I guess I don't want to mirror that, so I'm just going to hook them up differently. And also, I guess I could do the actually going through. I mean, I think this is one of the reasons, like, you could ask yourself why they're actually going through the chip with the pins like that, right? Where 6 is connected to 1. That's going to save you from doing all the common mistakes with ESD stuff where you connect the ESD protector, but then connect something else like closer to the ESD source. So if you do it like this, then you just physically can't. And so it's kind of the chip manufacturer, I guess, kind of protecting you from yourself. Let's see if that ends up the right way around, or if I had a brain bug. Okay, I think we're the right way around. Yeah. Oh, but we're not the right way around that way. Yeah. So I guess we want to do like this, and then we're not the right way around anymore. Although I guess I could just go like that, and then mirror this horizontally. Was the X key is horizontal? Yeah, there you go. And then update again. Now we're the right way around. Okay. Okay, yeah, this is working out great, because then we can just do whatever works here. So is there anything else connected to this that needs to go in? Yeah, I thought so. So we can put this guy in here in the row, and then we can do this guy, and then everything kind of works out. This is down here. This one I might have forgot. Oh yeah, this is the positive. Oh, wait, no, they are just up and down. Okay, so I didn't forget that one. It just naturally goes here. Okay, so now we got, I hate it when it does this. It's like snaps to the grid differently based on where you grab it. There you go, there we go. Okay. See now, once we got them all lined up in a logical way, we can just go down here, smack some vias in there to make sure we get good ground connection. Oops, did I not hit V? Am I too close? Hold on, why is it not? Why? Oh, because there's a pin there. Duh. That's why it's not VAing. I guess we could, yeah, I guess we'll just go here to VF for the ground. That's actually not a very high amperage ground anyway. Are we going to go that way, or are we going to... We'll do the beautiful thing. Route them next to each other, even though it doesn't actually have to be a diff pair or anything. What? There we go. Okay. So, I think 3.3 volts. This actually should probably be analog 3.3 volts. I shouldn't be biasing to something noisy. Although through a 10K, like, how much noise are you going to have coming through there? But... Oh, that means I got to do the analog. I guess I'll just thread it out of there. Let's see. VDDA for analog. Oh, it's AVDD. Am I confusing people too much? Yeah. Should name it AVDD because that's what the pin on the chip is called. Then nobody gets confused. Okay. Up one. Hierarchical sheet pin so we can get it out. Put it there. And then we can go like this. And like this. It's a little bit ugly. I think I'm okay with, no, I'm not okay with that much ugly. So let's use G to move this over to like that. Like that. We could also just kind of move this down because it doesn't look that good. There we go. Okay, so that Is that logical enough? Yeah, that's logical enough. The net on the board will take the AVDD name, so you don't actually have to give it like an extra label. It's going to be clear what it is on here. Yeah, it's called AVDD. So yeah, we got that the right way around. I guess am I cool with it going up like that, or do I want to make a... Because the digital VDD is just kind of over on the left-hand side here, right? And we could do a zone of the analog VDD. Is this the VDD one? Yeah, or the 3.3 volts one. So we could stop digital plus 3.3 volts here-ish. Let's get that somewhat. That. Now let's do a new pour starting what, here, leave a bit of a gap. And we want ADC AVDD, and we want it on this layer only, because that's the layer we're doing the voltage stuff on. Because we did the ground layer close to the chip on the bottom, right? So this is, green is the upper inner layer, right? Why is that snapping to that? That's stupid. Oh well. Hit the B key to refresh. Then we just need to via this thing out and smack a via, say, here and right at the edge of the... And now we should have all the AVT. Yeah, now it's connected through the plane. We didn't really need to do a plane there because we just have the stuff here anyway. Oh well, being a little paranoid is not always a bad idea. I guess this guy here could go down like this. That would be a little more... Could actually even go all the way over here, right? I mean, it's decoupling that pin. Yeah, let's take this. 3.3 volts is probably not going to be all that noisy anyway, because we're not like driving big loads or anything. Just to be sure that no one can find any nitpicks on us. Famous last words, obviously. Yeah, let's put this up here, because that's actually the U4. And so C20, yeah, okay, so that's capacitor. Yeah, moving those around. Oh, and then we don't have a problem being close to the edge of the board. Because this chip looks like it's a lot closer to the edge of the board, but in reality, the pins are only going to go to about here, or possibly even like here, right? Whereas here, the end of the capacitor is going to be like here, or I guess this is a ferrite bead. It's going to be like here, and it's also going to be a lot taller than the pins. So yeah, we can make some more space between us and the side of the board. I'll just put this on the end of that. Not that we actually really need it to be that far down, but it looks better if they're all same. Whoa, what did I do wrong? Guess I was violating some DRC rule. That's a disadvantage to G. It doesn't actually do it if you violate some DRC rule. There we go. Smack the VIA in there. There we go. That's nicely tacked down to the ground plane. So what do we got here? Oh, we got the 5. Why do we have 5 volts? Why do we have 5 volts? So that's what? That's this thing. That's the upper 5. Oh, because it's the USB. We're using the same component as USB, and we just copied it over. Now, there is a reason to have the positive rail in here because they're, clamping down to the positive rail, as well as this TVS diode, right? But the decoupling capacitors on the 5-volt rail are gonna help us. I mean, I could theoretically just leave this off and let the clamping diode here in the middle do all the work. Yeah, I think I'm just going to do it like that. Um, if you're intentionally not connecting something, it's good to use Q. I don't know why Q. I remember it as quiet, but that's probably just a bad way to think about it. Um, but anyway, so the blue X basically in KiCad, which you can do with Q, means it's not connected. And if you're intentionally not connecting something, that's good to tell the people visually that was actually on purpose. Okay, so now we don't have that pin connected anymore. That's great. And so we're running out of things to connect. Okay, let's do those, and let's tack this to ground wherever we can. Tack this to the ground layer. Okay, what do we? Oh yeah, now it's time to route the SPI because now I know that the analog stuff fits, so we aren't going to need to move the chip. So let's do some SPI routing. CS, okay, CS is down there, so I guess this one's going up. So I think I'm going to route this one around the back. Oops. Delete the track. When it does weird stuff, I usually just delete it and start over. I went too far into there, I guess. Yeah. Why don't I just... Yeah, D should be able to move it. Yeah. What's up, KiCad? Why are you... There we go. And then grab this one with D and move it over here. And then down. Why is KiCad doing some weird stuff? Oh well. And V without anything selected, so it switches back to the top layer. That's a good shortcut to use. Okay, oh yeah, that works out pretty well, or not quite. Let's see, D that one up a bit more. Do I have the, no, I don't have the grid set high. I'm not sure why it's acting weird. That's why I call myself an expert, so I can confidently be confused. Okay, get those tacked down. Let's see, so what else do we got? Okay, this is some kind of chip select or something. Why is that called GPIO14? That shouldn't be called GPIO14. Here, I've been telling everybody to name their nets, and then I leave something called GPIO. Data ready. Okay, so the reason why it's calling it GPIO14 is on this generic block over here, is that's what it's called. But in our application, we're using that for the data ready signal. Yeah, I guess interrupt is actually probably better. I guess we could just go with the RDY. So KiCad doesn't know which one of these to go with, but if you actually label it, right, either this one or I just hit L. Let's what do we call it? Oops. What's Microsoft doing with these stupid ads if you kind of swish over the side of the screen? So let's call it DRDY and just smack that on there because that's a tiebreaker. If you like named it rather than it taking it a name from a hierarchical sheet pin or something, then it will keep that name for you. And so now it's called DRDY. And so now I know what it is. What a concept. Yeah, it's good to be clear what your nets are by naming them as schematic, because then you don't, out of not knowing what a net is, do some stupid stuff with, a high current or high frequency net and not realize it, or, any of that kind of stuff. So why do I have... Oh, that's going to the top layer. I get it. Make that thicker. Okay. I guess we want to put the via close to the decoupling cap. It doesn't actually matter in that case. I'm being too pedantic. Oh, it does matter, but it's not, doesn't mature. Damn it, Microsoft, what the hell? I paid for Windows, now you're still showing me ads. Time for a Linux upgrade or something. Yeah, I didn't really learn Linux along with everyone else because back then you could just get PCB software with Windows, and so that kind of tied me to Windows. All the cool kids that were just doing software all learned on Linux. I'm okay with it now, but yeah, it took a while. There's certainly some concepts that I didn't grasp initially, where if I just learned the concepts first and then played around with it, I would have gotten a lot, yeah, gotten uh, gotten good a lot faster, put it that way. Um, but I am impatient when I learn things, so that's why I kind of do it the wrong way around. But guess you never know. Like I think I um, have some more unique opinions than other people because I learned things the wrong way around and they learned it the right way around, and so I had some, you know, 99% was harder, but 1% is some extra insight. I don't know. Maybe I'm just making excuses for my personal flavor ADHD or something. Anyway, this is getting really off topic. Okay, I think we routed everything. If you do N, it'll show you the next net, and if N doesn't come up with anything, then you're done. So that's actually another good keyboard shortcut. So I think we probably should start placing the silk screen because our silk screen is terrible. I guess that one looks good. So what? C7 is where? C7 is there. That one's actually not bad either. How did the grid get all the way up there? I think there's some hotkey that changes the grid that I keep accidentally pressing. We don't want a big grid. Silk screen can go anywhere. Printer doesn't care. Okay. So this is that. So okay, now we're getting a little harder. Well, why don't we make this silk screen smaller? JLC can do considerably smaller than 0.8, but like I said, I want to keep my options open as far as potential manufacturers, although, you know, a good portion of my net worth is chips in the JLC PCB warehouse at this point, so maybe I'm just kidding myself ever getting away from them. I mean, that, yeah, it is logical for them to have all your chips sitting there ready to go where they are going to be needed when you use them, but it definitely binds you to JLC. Which is obviously very savvy business decision on their part. I think whoever tries to do a JLC competitor definitely needs to team up with somebody like Avnet or DigiKey or something, and co-locate with their warehouse. So that, I mean that's one of the reasons why JLC works so well, is because you have the components in their warehouse like right next door, and yeah, it makes everything easier. And we'll actually probably see that. Although I haven't been doing so well on time. We're what, an hour in, and we still aren't selecting components. So I'm going to try and go faster so that we can finish up this time. Okay, wait a minute. So this is the bottom one, then comes that, and then comes that. Is there a way for me to do this logically? Let's make this one small to give us more room. Yeah, it's funny as I get faster at other stuff, Silkscreen ends up taking more and more of the board time, or the board development time. It's kind of ironic that, although you have that all over the place, right? Like, uh, I don't know, spices back in the day going across the ocean. It used to be like 99% transport cost, 1%, sometimes not even 1% was the original cost of the goods in Asia. The spices in Asia. Um, and then things started going down in price, right? Like, yeah, diesel engine, um, cost of defense went way down in the Bretton Woods thing, and everything goes down, 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 down until at some point, physically loading and unloading goods become the bottleneck, right? Hence the invention of shipping container, right? Like way back when, nobody cared, right? And we've been successively making PCB designs go faster and faster and faster with, the edgy concept and better CAD tools and whatever. And at some point, silk screen's gonna be the bottleneck where it really wasn't. And my first boards took me weeks, months, right? Uh, I guess a lot of that was reading data sheets and whatnot. Okay. Okay, there's already one there. So can I maybe put these over here? I mean, I guess they won't be readable with a assembled board. But anymore, you can just look at the CAD. I mean, the justification for silk screen is also going down and down and down. I mean, whenever I start messing around with a board, I almost always just open it in CAD and look where stuff is. I don't usually look at the silk screen anyway. I guess sometimes it's easy. Like what you should definitely do with silk screen is when you have like a connector, like do the pinning as a silk screen. Actually, I have my colleague asked me, like, yeah, you have like that fallback serial port on the Pi compute module. How do I access that? It's like, oh, okay, well, 115, 200 baud. Shit, how was the pinning? I'm not at my computer right now. Yeah. If I had done that on Silkscreen, as if I had practiced what I preached, I wouldn't have had that problem today. So, yeah, it does actually come up. I'm just rambling though while trying to fix the silk screen. Okay, this is still a problem because I can't go on top of that. So let's make this smaller too. And then we'll do the design rule check and it'll tell me all the other 50 places I screwed it up. Okay. Design rule check. Oh, it's going slow. Why is it going slow? Oh, well, that's a lot of... Oh, it's talking about the vias. I didn't... Yeah, let's exclude all of those. Ignore all annual itch violations. There we go. Okay. Whole clearance constraints. Oh, yeah, it's kind of the same thing again. I'll look into the vias. It might not be right. But for now, we just want to be done. I'm sure somebody can manufacture this board with vias like that. Ha ha ha. No, I'm pretty sure that JLC can do it too. I just didn't set up the board right. Edge clearance, yeah, but it actually is that close to the edge, so let's exclude that one and that one. Let's go through all the errors first. We seem to still have a whole bunch of errors. Board edge clearance. Oh, it doesn't like the... Yeah, those are definitely too close to the edge. So DRC saved us. Yeah, so let's switch to the bottom so we can see the problem better. Yeah, that definitely can go closer here, using G to scooch it with DRC check updated in with. Oh, here we also forgot a via. I was talking about that a couple episodes ago. You know, you have the plane automatically connects everything, so you forget the vias, because you definitely want to go to the plane close, because the chip's other, the chip's ground is going to be here connected to the plane, so they're connected to each other through the ground plane. So if we don't connect it here, then we're going to have a huge loop rather than a tighter loop. Yeah, here I think again we should be doing a lot of vias, which I forgot. Although I guess that one probably needs to. Why don't I place that one later? Because I do need to scooch these first because they're way too close to the board edge. Go G and then yeah, maybe we do unroute some of this stuff and then scooch these guys over like that-ish. Do I care? Yeah, no, that's far enough from the board edge. I'll rewrite that and make that look pretty. Doesn't actually matter. Okay. Are those far enough from the board edge? Let's run it again and see what we got. Hole size out of range. That's again more via stuff. Thermal relief connection. Oh yeah, I think I set it in the board to do 2 spokes rather than 1. That doesn't matter. We're not running any high currents. Okay, unconnected items. Oh yeah, I guess I broke that connection or something. Wait a minute, where is the unconnected item? What's the deal, guys? Oh, yeah, okay, I get it. This pin wasn't connected to that via. Oops, doing the wrong thing here. Although, why is that giving me a warning? No net found for component U1 found. Okay, well, I don't care about that. Okay, no more errors, then we can start looking at. Oh, was I just demonstrating something with that track? Oops. With the streaming view, my mouse handling is confused because it center point of the monitor is different the way my streaming setup is, so that's why I'm looking like a duck out of water. Or fish out of water. I guess ducks are fine out of water. Not even my analogies are good today. Anyway. Okay, silk screen. Let's zoom in so when we click on it, actually. Silk screen to board edge. Oh, that's underneath of there. Oh, we haven't even made the bottom pretty. Why don't we just do that first before we start looking at DRC stuff? Because the bottom silk screen. Now, how did I change this all the way up to there again? I'm not sure how I'm doing that. It's probably a layer 9 error or whatever that is, the user, as in me, error, but I am confused by that. Okay, let's see. What is that connected to? That's connected to that. And we definitely have some space to just go one after the other. That's the big one, so let's put that over next to pin 1, and then nobody's confused. Okay, these are going to be more interesting. Let's make this one smaller. Yeah, we're doing okay on time. I definitely need to do some more components and then show you guys how to order. And then we'll be through an entire design. If I didn't think there was just endless work for people who are good at making PCBs right now, especially in the West, then I would be worried about teaching y'all how to do it so good. But yeah, no, there are so many companies out there that have such outdated designs. There's enough dinosaur meat for everyone. And also, if we solve all these problems, then I mean, a lot of problems stem from like bad, outdated sensor data, or not enough sensors, not enough ground truths. I mean, arguably even like a lot of political problems stem from that, and a lot of societal problems because nobody actually knows what the ground truth is because no one's actually measuring it. So let's just make measurement cheaper, and then we'll spend less money on stupidity because we'll actually have data. Rant ended. Ha ha ha. Yeah, that's kind of a lot of my sort of motivation in doing this kind of work is, you know, if people had data, they'd spend less time fighting about what the data might say. Okay. Ah, I'm doing the wrong thing again. One. Okay, what is that? R7. Oh, yes. R7 is also incredibly stupid on my part. So, shouldn't it be FB something rather than R? Okay, am I just going to put it under the chip? That's kind of a stupid move on the one hand, because when the chip's mounted, you aren't going to be able to see it. But on the other hand, we're so reliant on CAD now anyway. And in CAD, you can definitely see it. Oh yeah, that one definitely needs to get smaller. So let's do that. If I was a proper streamer, I'd edit this video for the post-production and do all this alignment stuff like really fast, and so you guys don't have to sit through it. Feel free to like scroll forward or whatever in the video if you're not watching this live, or you can suffer with me. Okay, almost done here. Thank you guys for suffering with me. Anyway, oh, that's a hole, so that's going to be drilled through the. Yeah, why don't we make this one smaller too? Drilled through the print on the board. Don't want that, so it's definitely warning me correctly. What's with the weird snapping? There we go. Okay, R3. Oh, yeah, same hole problem again. Well, here we'll just put it on this side of the hole. And then, why is it warning me about this? Like, that's kind of half off the board. Why? I don't get it. Okay, let's run this again. Yay, we're all good. Except for the via thing, that might be a problem. But if it is a problem, you can just picture me rewording the board with bigger vias. Okay, so we got the board rooted, we got the schematic done, then board rooted, and if we go back to the schematic, we can see that for some of the components, we have the LCSC numbers. And normally, from the edges, we would have gotten all the other LCSC numbers as well. But we changed the size in the edges. The size of the components were all 0603. Since we have a tiny board, we made them smaller, and so all the LCSC numbers are invalid, obviously, because they were the LCSC numbers for bigger components. So now we need to select components, and a lot of them. So let's switch back here into the board view, and we have this plugin called JLC PCB Tools. It's some open source guy who is my personal hero because he made a cool plug in. So that's what we're going to be using to find the components on JLC. So we got 100 nano, and we want to select alike parts because we got a bunch of 100 nanos, and then assign LCSE number, and it already knows the keywords to look for, and basic parts are going to be cheaper to mount at JLC basic in terms of JLC PCB component placement and whatnot. Basic means they have it already mounted on a machine somewhere in their line, so you don't have to pay for them to put the roll onto the machine, which is like $2.50 or something like that. So yeah, we definitely want to go with the basic components whenever we can get away with it. And also the Samsung capacitors are good. We don't need the expensive ones. Here we can see the price. I mean, okay, it's in large amounts. Oh no, these aren't even large amounts. Oh my God, it's like a tenth of a cent versus 0.4 cents. But the difference is the voltage rating, right? 16 volts versus 50 volts. Here, there's nothing on our board that's over 5 volts, so we can just use the 16 volt ones. And all of the 100 nanofarad capacitors together are less than a penny. China is amazing sometimes. Okay. Select delay parts. 12 pico. CSE. There is a basic part, and it fits our specs. Let's go with that. What do we have here? Select alike. Yeah, we have multiple ones of them. So CSE. Yep, there we go. It's a Samsung. What is the? Okay, it's X7R. Like the COG whatever has a better voltage derating, and since we're in like an analog input sampling line, that might actually be interesting if the capacitance changes over voltage. On the other hand, this is a thermocouple, so the voltage range of change is going to be tiny, and so we don't care. But if you're doing like analog input circuits, you do have to worry about capacitors changing capacitance based on voltage. Like if you have a sine wave going in and you have some filter, then the bottom of the sine wave might be closer to 0 volts or whatever, and so it's no longer a sine wave after it goes through your filter circuit because your capacitor has a different capacitance based on charge. I mean, that's one of the major parasitic effects that you don't like from the ceramic capacitors is the uh, voltage bias, like the change of capacitance over voltage, commonly referred to as derating. I'm not quite sure why, but yeah, that's something to look out for that a lot of newbies kind of trip over. Like the capacitance of a ceramic capacitor is its capacitance at 1 volt of charge, right? And if you increase the voltage, the manufacturer will give you some chart, but like for some capacitors at 10 volts, you're already down to like 15% of the original capacitance at 1 volt. So yeah, it can really bite you. But in this case, we don't care because it doesn't matter because our voltage change is tiny on our analog input. Okay. Bip, 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 bip. I think it's doing everything right here. That's the cool thing about this tool. Also, like, note that I am using the decimal point here, as is JLC. That's why they're kind of lining up well. If I had been naming them like 2U2 or something clever like that, it would have saved me typing, but it would have not saved me time because I'd have to be correcting it here every time to search the JLC component database. Okay, so we got those. 100 Pico. What is the 100 Pico C16? Oops, got this open already, and it's somehow huge. Okay, C16 is... Oh, that's to the shield. Okay, so we do want a pretty high voltage one on that. Um, Although I guess the shield is connected to something groundish on the PC side, generally. Yeah, it's not going to be a problem, I don't think. So let's just see what JLC suggests. 50 volts. Yeah, it'll be fine. I mean, I guess if this was... Like, you might want to go with a higher voltage rated capacitor here. I think this is actually, no, I did, thinking about it, I think this is actually wrong that we're going with this tiny component. I think we should make it bigger. Because you do have situations where the shield is a lot different than the rest, and we don't have any EMC on the shield, right? So somebody touches the shield when it's not connected at all on the other end, which is probably the more common touching thing than we're frying this capacitor. Yeah, look, so it was good that I checked what it was. Yeah, so this thing, if we just make it bigger, the voltage will, tolerance will just go up with the standard components in JLC. My voice is kind of going out. Sorry about that. Okay. Why is KiCad so slow? Okay, let's try something like a 805. Can we fit that on the board? I mean, that's probably going to be in the kilovolt range at 100 pico. Let's see, where can we fit? Oh, we got plenty of room down there. Let's just put it like here. Oops. If you select the layer that you want, then it's easier to click on stuff, because I was getting like silkscreen. KiCad didn't know I was on a different layer. Well, which layer do you want, right? So if you switch, that's another tip. Well, you do usually like figure that out intuitively. Okay, so now with that component hugified, I'm sorry to foreign speakers, hugified is obviously also not a word. Oh, it's still 50 volts. Okay, so I guess we do need to look at extended. And then, do they have a voltage here? No. Okay, so I guess, and what I usually do to make sure I'm not going for some obscure components, I just start by ordering this by the amount of stock that they have. Because, you know, if JLC has a huge chunk of stock, it's not going to usually be a weird, unavailable component or anything. So kilovolt looks good. Prosperity Dielectrics. I've never heard of them. I think I have heard of them, but I don't know if I have a positive association. I guess this doesn't really matter, because even if like you blow this, the EMC just gets a little worse, and it's probably still fine. Oh, we're already down into the 0. So why don't we just go with the Yago for 500 volts? That should be okay. Because with a human body model, when you're touching it, okay, it's like 2 kilovolts or something. But it's 2 kilovolts at some capacitance. And so you're just going to be a divider with the capacitor. Although I guess you'd still be over that with the divider. Do I want to put ESD? I'm just going to go with this thing and hope that they're fine. again, if we blow this thing, it's actually not end of the world, so I'm not going to put a whole lot of time into it because I want to get done with the stream in time. Okay, 10 micro. Oh, those are just decoupling stuff. Yeah, that's decoupling stuff. Let's turn extender back off and go with the cheapies. I mean, not that the capacitor is cheap, but it's cheap because the JLC is not going to charge us for going into the warehouse and getting a roll out and putting it on the machine. Okay, 10K. We don't need anything special. We can just go with the Uni Royal. That resistor making company, I don't know how they optimized everything to make them so cheap. But I can understand why they are. Oh, wait a minute. Yeah, sometimes it gets a little confused if it's like 1K and okay, 51K also has a 1K in it. It's just a text search. $200. Don't need anything special there either. Don't need anything special there either. Wait, why is it freezing up on me? Don't freeze on me, I'm live. Okay. Oh, the 0 ohms is going to match the world, right? Okay, but there it is, pretty close to the top. That's cool. Yeah, the component, this plugin, the author recently figured it out with the turning the R into ohms while searching JLC. That is a godsend. I should buy that guy another beer or two. He makes my life so much easier. Always be nice to your open source guy. 1 ohm or 402. Why aren't there any basic components at 1 ohm? Or is this the streaming software messing with my... That's weird. That's 51 ohms. That's 1 ohm. I wonder why that one isn't basic. Isn't 1 ohm kind of normal? Oh well, I guess maybe it is in bigger sizes. That's just because we're kind of abnormally small with our 402s. Well, 402 is actually super common. Okay, so they don't have 10 megs either. Well, then we'll go for the extended ones. Oops, I didn't mean manufacturer, I meant stock. There we go. And just go with the same manufacturer with all these things. I mean, Yego's fine too. It's, yeah, we don't need a whole lot of hard to find specs. Okay. Is there a basic one? No, there's not a basic one. So, nor flash. Use on 2 times 3. Yeah, I think that's the right one. Yeah, we're good. This one, so let's see. Oh, no basics. Okay. Well, yeah, the one with the giant stock is definitely going to be the right one. I don't think they're gonna. What is that? 100,000 of them. Yeah, they'll sell them. I mean, it's a good microcontroller, right? Okay. This guy comes in different packages, so we want to make sure we're getting the right one. And the number of, yeah, okay, so it's definitely not a QFN. TSOP 16. Yeah, that looks like the footprint. Yeah, we're good. Oh, and it's even cheaper. Well, that's cool. We're starting at 1 port, they're only 159. That's a good ADC for 159. Okay, and these little suckers, SOT236. They have most basic? No, they don't have most basic. Okay, well, let's see. Top stock. Oh yeah. What was this? I think it's that 10 to 15 cents, and they're 10 cents from ST, but they're cheaper from. Do I trust the Chinese manufacturer? On this episode of Can You Trust Random China Stuff? You actually can, surprisingly often. Like, they've been getting better. I think I'm still gonna go with ST. Because, 10 cents is not gonna break the bank. And I'm sure I'll pass EMC with ST. Oh, I forgot to do the select alike components. So we have to select ST again. That's the same part number, right? Yeah, okay. Oh, and the crystal. Seems like that should have come in through the... Why didn't that come in through the edgy? Oh, I'm using an older version of the edgy. Anyway, normally that component should already have an LCSC number because it came in through the sheet, right? So 12 megahertz. They have a basic one, SMD 3225 4-pin. Let's check if its footprint is called something with SMD 3225. 3225. That's the millimeters, or yeah, tenths of millimeters. That should work. Because I know it's a basic component just out of experience that works with the rp2040. Like, we have a bunch of them in the field already. Okay. Looking good. So now that we have all of these components selected, we can just hit generate fabrication files. Yeah, I never do the JLC placeholder. I just let them put it somewhere on my board. I don't care if people see that I've ordered my stuff from JLC. Okay, so we got another half an hour. So let's look at the fabrication files. They should be in here. And then JLC PCB, and then production files. So here we've got Gerber, which is like the standardized PCB order format stuff, which is basically just pictures of every layer. It's like some vector graphic format. So if you're ordering just the boards, then Gerber's enough. But we want to also have the machines place all the components and whatnot, and that's why we need the BOM and CPL files. So the BOM file, you look in the BOM file, it's the BOM, yo. Okay, terrible 90s humor. It's a CSV file with all of the components. BOM stands for bill of materials. So let's look at the CPL file. What's in the CPL file? The CPL file is the component. I'm not quite sure why they need its value, but the coordinates here, this is the important part, right? And whether it's on the top or the bottom. This is going to allow JLC to know where our components go on the board, like where we put them. And that doesn't always work, but we'll see how to correct it momentarily. So let's go to, I think this is off screen, so why don't I make a new tab and then pull the new tab on screen. There we go. Although I don't know if I have stuff in my card part or history that you can then see on JLC that's under NDA? Probably not, but why don't we just not use my account? Gotta be respectful of designs we made for customers that don't want the world seeing them. So let's go to order now. I think I can just do the whole order process without actually signing in. Okay, so we got the order started on JLC. We can just drop the Gerber on there, and they have an impeccable system of figuring out what board you need. Yeah, look, it realized it was a 4-layer board, dimensions, all of that. We just need normal industrial consumer electronics, nothing aerospace medical. That's just going to drive up the price. Oh, look, yeah. Although I would have thought it would be, oh yeah, it's TG155 and all 4-well Kevlar test and blah, blah, blah. So, this TG rating of the board, that stands for temperature grade. That's like how hot the board can be before it starts doing weird stuff. It can often be hotter than that for short periods of time. Like, when it gets soldered, it's obviously going to be more than 155 degrees. But, if you're in an environment where it, often gets hotter than that, then you want to go with a better temperature grade. I think the standard is like TG 100 or something, and this is Celsius, right? So if you're using chips that are rated for 120, you might want to worry about your board. But in this case, we do not care. Deburring edge rounding. Oh yeah. That doesn't change price, does it? Oh, it costs us 20 cents. Wow. Yeah, what they mean by burrs are like pieces sticking off the PCB. I guess I don't really care either way. But if you're doing panels, panels like multiple at the same time, which is going to help our production when we produce it later. Right now, we're just doing normal everything. 1.6. I think I'm just going to go to a 0.8. 1. Yeah, 0.8. Just because it's going to help it fit in the case better. Oh, yeah, here we can select the TG. Oh, okay, 135, 140 is the normal one. Oh, so I lied. It's actually more. And then the surface finish, the hot air surface leveling, is basically they dip it in solder and then they blow on it so that all the solder that's kind of sticking to it kind of gets pushed off to the side and then it's relatively flat. This one, it's much more high quality pads. Like if you're doing a lot of hand soldering, I would actually suggest getting this. And it's also, yeah, it's just generally a higher quality thing. So that's what that is. Like this is the galvanically plating other material on top of the copper. Because if you just leave the pads copper, then they're gonna corrode. They're gonna, the copper is gonna take oxygen out of the air and oxidize. And so, yeah, I mean, if you're soldering them immediately, then maybe it'll work. But if you're soldering them a month later, then it might start to not work. And definitely, years later, it might even corrode to the point where your, resistance in your across your pads is going to go up and all that kind of stuff. So they want to cover the copper. I mean, the copper is covered with the Stopplack. What is that in English? The whatever that polymer layer is over the top of the board that covers the normal tracks. It's usually green. But where the pads are, it's not covered. And so we need to cover it with something that's electrically conductive and plays nice with solder, but is also doesn't corrode from oxygen in the air. And so either hot air surface leveling or um, uh, electrochemical plating. Um, yeah, if you're using a different solder than the solder that they're using for the hassle, um, that can also do weird stuff if you're like hand soldering some of it. Uh, yeah, that's basically the extent of my experience with the two. Add our copper weight. We don't have strong currents or anything, so we don't have to up these at all. Specify for layer sequence, no. I've never actually had them do the layer sequence differently than just the default. So, yeah, I don't think that actually does anything. I've ordered a lot of PCBs with JLC. Uh, yeah, if we were doing high frequency stuff, we might want to go into the impedance calculator and figure it all out, right? But we don't care for this design because we do have USB, but only really, really short tracks, and so it's not going to be a problem. So look, they're already plugged for, guess what was originally $2. I did a different height. Um, Wait a minute, something made it more expensive somewhere just by me selecting a smaller board, and now it doesn't go away again with the bigger board. That kind of frustrates me sometimes with JLC, but I guess it's not necessarily a easy problem to solve. Okay, yeah, here's where they're going to ding us with the vias because we selected this. So that's going to be, oh, look, see, that got way more expensive right there. So that's, yeah, that's why we should have done bigger vias like, to this spec. But I don't care right now. Let's see. So the edge plating is sometimes interesting if you want like a board with the copper like around the outside. Some people do that for like high frequency stuff. It's yeah, castellated holes are these holes. Those are pretty cool. Sometimes like I think in a previous episode we were doing like a land grid array with castellated holes going to go on the top. Um, we don't need any of that for this design. For a while, where Kelvin tests, oh yeah, that's probably because of the small vias. That basically means that they have like flying probes that connect to your PCB in different spots and make sure that stuff is actually connected together, that is theoretically connected together. Paper between the PCBs, well, we're going to have them manufactured with you guys anyway, so don't need that. High precision silk screening. I don't care if the silk screen's messed up. If you want to do pictures on the silk screen, this one's pretty cool. Package box with JPCB logo. Well, obviously you want the JPCB logo on there. That's how you know it's PCBs. Why would you ever want a blank box? I think a lot of other PCB manufacturers just a wrapper around JLC at this point. Final inspection. Yeah, I don't need any of that kind of support. So, assembly. Let's turn assembly on. So, we want both sides. Look, it's getting more expensive. Um, I often just do two because I don't actually need five. And, yeah, the components cost a bit of money. I guess it doesn't really matter. Add rails, fiducials, added by JLC, that's fine. Fiducials are the little dots on your PCB, which help the uh, pick and place machine find its orientation, or other things find its orientation. And then edge rails are like if you are sending it through the oven, then it's going to be, you know, a certain width. So they'll just add some PCB around the outside so that they have standard widths. Foam parts placement, no, that's fine. Haven't really had problems. I've just let them do it, and it's enough boards at this point that I'm confident they'll get it right. Guess if you had really expensive components, you probably would want to do that. Part selection by customer. I haven't actually tried letting JLC PCB select the parts. I'd imagine it's some AI. It might be good. I don't care yet. Okay, so now we can just go to the next one. Now it does want me to sign in. Hold on, let me sign in off screen and see if you guys can actually see anything that's oh, it's making me do a recapture thing. Okay. I think that's fine. Oh, and make sure that there's nothing visible on my account that I don't want to stream. Okay, so they're confirming that this is the top side and this is the bottom side. Yes, those are the top and bottom. Okay, now we want to give them the BOM file and the CPL file so that they know where things are. Let's process, and they're going to ask me about all the stuff that I didn't select stuff for. Yeah, it doesn't have. Okay, yeah, the test points. Well, they're hand solder anyway, so we're just going to go. I mean, yeah, it doesn't have positions for components going on the test points. Well, yeah, there are none, at least for you guys. And now, okay, I guess you can see what kinds of parts I already have in stock, but that's fine. That's not trade secrets. Yeah, and the next one, you guys still can't see anything too spicy. What's it saying here? Oh, okay, yeah, so... Oh, okay, so yeah, okay, so JLC is taking care of that one. I thought I actually had those in stock. Yeah, the things like the debug connector, obviously nothing gets placed on it. Okay, so now we're in the view where we have to rotate all the components correctly. And as you can see, the rotations suck. So we want to flip this up to where the pin 1, which on the JLC part is going to be purple, is matching the pin 1 from the footprint, which KiCad has graciously made a little arrow in the newer versions. Used to be sometimes wonder what pin 1 was, but now they made it easy. So we got those rotated. Sometimes they're also off center, so you actually have to drag them into place. Look to the bottom, see if that ever happens. No, I don't. Doesn't look like any component has that problem on this board, but that can definitely be a problem. Wait a minute, why didn't I get errors because of the silk screen here? That's messed up, the silk screen. Oh, because I didn't do a DRC after I put this component down. Keep calm with DRC. I think I actually own a t-shirt that says that. I also own a t-shirt that says run DRC instead of run DMC. You can tell I forget to DRC a lot. Um, friend of mine was at the border of the Democratic Republic of Congo, and on his t-shirt it said run DRC. And he had to explain to them what a design rule check was, and that apparently wasn't easy. I think eventually they just said, okay, stupid foreigner can go anyway. Yeah. They'd understood that it wasn't hostile to them. I thought that was quite funny. Okay. Yeah, it looks like we got pin ones everywhere we need to have pin ones. And then, hold on, let me do this off screen just to make sure we don't see, because I think I have stuff in my, okay, yeah, not spicy yet. It's just confirming all of our ordery stuff. And then here, they're going to have you like select what it is as for the customs, but they don't actually let you select what it is well enough to where customs is actually happy. And so, yeah, customs probably going to ask you anyway. So I'm sorry about this stupid doing it off screen, but I really don't want to show someone else's design. Okay, yeah, the other design that you can see here in my is our IP, so that's fine. So yeah, so here's where you do a secure checkout, and then we would be done. And seeing as we're 10 minutes before the end of the stream, it looks like we got done a little early. So that was thermocouple start to finish in 2 episodes. That's what, 4 hours worth of work. If I was actually making a product, I obviously would have done the vias differently than we did, just to keep the cost down. And let's see, what else would I do differently? Not much, really. I mean, you could manufacture and sell this uh, in 4 hours of work. That's not bad. Obviously, we have to do firmware for the microcontroller, and um, that's going to take more than 4 hours. Although we do also have like a uh, uh, good library system where you can kind of mix and match and put stuff together. It's called Quasier, if you want to check it out. Quasier.io. Uh, yeah, I mean most of the meat of that is actually someone else. I did start it, but someone else has taken up the torch, and yeah, so that's what we use to program the rp2040. Uh, so yeah, communication over USB, and even debugging over USB and all that kind of stuff is just in there already. And SPI is in there, I think, in the open source version. Yeah, it should be in there to talk to the ADC. So yeah, what you'd have to do is set up the actual ADC commands, but that's not going to be hard because there are only a couple of those. So yeah, that's maybe a week's worth of work to get the firmware working. But then, a week plus 4 hours is not much for product. Uh, so yeah, that's why we're, comparatively pretty cheap for quality engineering work we do. We got it all set up so it's circuit Legos so that you can uh, benefit from all the other similar designs that we've ever done. Power of abstraction. It's funny, people understand that in software. People don't really understand that much in hardware, so we're kind of, I wouldn't say completely alone. There are some other enthusiasts, but most other companies don't have things like the etchy board concept or that kind of stuff. And yeah, that definitely helps us be agile. So I think there's some cutting edge knowledge there, maybe. Uh, um, yeah. Hope everybody's having a great weekend and hope you didn't miss me too bad last week. I'm curious what the YouTube algorithm's going to do with me missing a week. I've heard that's like terrible for your algorithm, but yeah. Oh, by the way, the algorithm likes liking and subscribe, so do that, obviously. I should have said that earlier in the video. Somebody told me, like, I've been saying every episode that I have no idea what I'm doing with streaming, and so I've been getting tips. And somebody was like, "Yeah, you got to tell people to like the video like way in the beginning when they just start." And YouTube really likes that. And it's probably like search engine optimization, where YouTube likes a different thing every week, and so none of the knowledge is right. Um, but yeah. Have a nice rest of your weekend, everyone, and I should be back. I might not be back next Saturday. It might be a routing on Saturday on Sunday again. But I'll have to figure out what we do. Oh yeah, no, we should do an Ethernet sensor next week because we've seen the Ethernet host side, and then we could see the Ethernet device side, and you guys can be all up to speed on that. And then after that, maybe we'll do a Pi compute module or something. And at some point, we probably should do some op amp stuff because that's interesting. Uh, like anymore, most stuff is digital electronics, and most stuff that's not digital electronics is some tiny edge of the thing which does the analog front endy stuff. Most analog front ends you can get uh, integrated into your ADC already, at least at low frequencies. Um, so yeah, a lot of the analog stuff is not. Um, I guess I wouldn't say it's not common. Like some people, like if you're designing military radar or whatever, then obviously we're going to do some analog. Although I guess that's all. I mean, the phased array stuff is FPGA. Yeah, I mean, the significance of analog stuff is usually more EMC, switching power supplies, and just uh, power integrity. That's where you get some analog stuff in there. But yeah, when you do analog stuff, it's still probably not a good idea to go transistory. Op amps are cheap and definitely decrease the amount of foot guns. For people that don't program C++, a foot gun is a thing that makes it easier for you to shoot yourself in the foot, right? Um, yeah, at some point we should probably do some more power electronics, like switching big MOSFETs and stuff. Uh, yeah, let me know what you guys want. I mean, I do have sort of a niche where I am at home, of which is the typical stuff. Like we do a lot of monitoring systems, so measuring physical values, either for monitoring systems so that people get messages when something's going wrong, or predictive maintenance, or that kind of stuff, or also environmental stuff, critical infrastructure. There's a whole lot of monitoring categories. But also, if you want to train AI on real stuff that's not video or text, then you actually need data that's not video or text, right? You're not going to have a video of a motor and be able to predict when it's going to break. You need vibration sensors, you need power signature analysis, that kind of stuff. Um, Same goes for like electrical chemical stuff. We're kind of getting into that a little bit with Montana State University. They're cool. I like them. Um, as have a partnership where I don't understand any of that. I just understand the electronics, so that's where the partnership comes in. So yeah, I kind of have a niche there. Like, I'm not going to do some big brushless motor designs or something. That's just outside my wheelhouse. And not. I guess to the very little extent I know some stuff about radio stuff, but that's mostly just to pass compliance with radio modules, like Wi-Fi modules or whatever. Um, Yeah, I mean, a lot of it's just you know, getting getting circuits done, getting sensors out there. So yeah, if anything you want any knowledge that fits into that, feel free to ask. Like I said, I'm doing this on my free time so that people can learn. I learned a lot watching people when I was starting out, and YouTube gives you the power to watch people in a non one-to-one context. So I hope this helps some people. The viewership has been going up, so that's good. As long as you guys keep watching, I'll keep making them. And take care, and bye bye to everyone. I hope you got value out of this, and I hope you have a great weekend. Bye bye.